Cerium is a chemical element with symbol Ca and atomic number 58. It is a soft, silvery, ductile metal which easily oxidizes in air. Cerium was named after the dwarf planet Ceres. Cerium is the most abundant of the rare earth elements, making up about 0.0046% of the Earth's crust by weight. It is found in a number of minerals, the most important being monazite and bastnäsite. Commercial applications of cerium are numerous. They include catalysts, additives to fuel to reduce emissions and to glass and enamels to change their color. Cerium oxide is an important component of glass polishing powders and phosphors used in screens and fluorescent lamps. It is also used in the flint of lighters. Characteristics. Physical properties. Cerium is a silvery metal, belonging to the lanthanide group. It resembles iron in color and luster, but is soft, and both malleable and ductile. Cerium has the second longest liquid range of any non-radioactive element, 2648 degrees Celsius or 4766 degrees Fahrenheit. Cerium has a variable electronic structure. The energy of the inner 4f level is nearly the same as that of the outer or valence electrons, and only small energy is required to change the relative occupancy of these electronic levels. This gives rise to dual valency states. For example, a volume change of about 10% occurs when cerium is subjected to high pressures or low temperatures. It appears that the valence changes from about 3 to 4 when it is cooled or compressed. 4 allotropic forms of cerium are known to exist at standard pressure, and are given the common labels of I+ or - to I. The high-temperature form, I-cerium, has a BCC crystal structure and exists above 726 degrees Celsius. The stable form below 726 degrees Celsius to approximately room temperature is I-cubed cerium, with an FCC crystal structure. The DHCP form of I-squared cerium is the equilibrium structure approximately from room temperature to a 150 degrees Celsius. The FCCI plus or minus cerium exists below about a 150 degrees Celsius. It has a density of 8.16 grams per centimeter 3. Other solid phases occurring only at high pressures are shown on the phase diagram. Both I-cubed and I-squared forms are quite stable at room temperature, although the equilibrium transformation temperature is estimated at circa 75 degrees Celsius. At lower temperatures the behavior of cerium is complicated by the slow rates of transformation. Transformation temperatures are subject to substantial hysteresis and values quoted here are approximate. Upon cooling below 15 degrees Celsius, I-cubed cerium starts to change to I-squared cerium, but the transformation involves a volume increase and, as more I-squared forms, the internal stresses build up and suppress further transformation. Cooling below approximately 160 degrees Celsius will start formation of I+ or - cerium, but this is only from remaining I-cubed cerium. I-squared cerium does not significantly transform to I+ or - cerium except in the presence of stress or deformation. At atmospheric pressure, liquid cerium is more dense than its solid form at the melting point. Chemical properties. Cerium metal tarnishes slowly in air and burns readily at 150 degrees Celsius to form cerium, 4, oxide, Ca plus O2 or CeO2. Cerium metal is highly pyrophoric, meaning that when it is ground or scratched, the resulting shavings catch fire. Cerium is quite electropositive and reacts slowly with cold water and quite quickly with hot water to form cerium hydroxide, 2 Ca plus 6 hours 208 2 Ca, OH. 3 plus 3 hours 2, cerium metal reacts with all the halogens, 2 Ca plus 3 F2 or 2 CeF3, white, 2 Ca plus 3 centiliters 2 or 2 CeCl3, white, 2 Ca plus 3 BO2 or 2 CeBO3, white, 2 Ca plus 3 I2 or 2 CeI3, yellow. Cerium dissolves readily in dilute sulfuric acid to form solutions containing the colorless Ca3 ions, which exist as a Ca, OH2, 9, 3 plus complexes, 2 Ca plus 3 hours 2 SO4 or 2 Ca 3 plus 3 SO2 4 plus 3 hours 2. The solubility of cerium is much higher in methanosulfonic acid. equals compounds equals. Cerium, 4, salts are orange, red or yellowish, whereas cerium, 3, salts are usually white or colorless. Both oxidation states absorb ultraviolet light strongly. Cerium, 3, can be used to make glasses that are colorless, yet absorb ultraviolet light almost completely. Cerium can be readily detected in rare earth mixtures by a very sensitive qualitative test. Addition of ammonia and hydrogen peroxide to an aqueous solution of lanthanides produces a characteristic dark brown color if cerium is present. Cerium exhibits 3 oxidation states, +2, +3 and +4. The +2 state is rare and is observed in some organometallic complexes. The compounds CEH2, CEI2 and CES have electride-like structure with Se3+ and delocalized electrons. The most common compound of cerium is cerium, 4, oxide, which is used as jeweler's rouge as well as in the walls of some self-cleaning ovens. 2 common oxidizing agents used in titrations are ammonium cerium, 4, sulfate 2Se, SO4, 3, and ammonium cerium, 4, nitrate 2Se, NO3, 6. Cerium also forms a chloride, CeCl3 or cerium, 3, chloride, used to facilitate reactions at carbonyl groups in organic chemistry. Other compounds include cerium, 3, carbonate 3, cerium, 3, fluoride, cerium, 3, oxide, as well as cerium, 4, sulfate 2, and cerium, 3, triflate 3. The differing properties of the 2 oxidation states of cerium allows cerium to be the most readily purified of all the lanthanides. Otherwise these elements are notoriously difficult to separate. A wide range of procedures have been devised that exploit the difference. These include, leaching the mixed hydroxides with dilute nitric acid, the trivalent lanthanides dissolve in cerium-free condition, and tetravalent cerium remains in the insoluble residue as a concentrate to be further purified by other means. A variation on this uses hydrochloric acid and the calcined oxides from bastnäsite, but the separation is less sharp. Precipitating cerium from a nitrate or chloride solution using potassium permanganate and sodium carbonate in a 1:4 molar ratio. Boiling rare earth nitrate solutions with potassium bromate and marble chips. Formerly used commercially was a method whereby a solution of cerium, 4, in nitric acid would be added to dilute sulfuric acid. This step caused cerium, 4, to largely precipitate as a basic salt, leaving trivalent lanthanide in solution. However, the finely divided precipitate was difficult to filter from the highly corrosive medium. Using the classical methods of rare earth separation, there was a considerable advantage to a strategy of removing cerium from the mixture at the beginning. Cerium typically comprised 45% of the cerite or monazite rare earths, and removing it early greatly reduced the bulk of what needed to be further processed. However, not all cerium purification methods relied on basicity. Ceric ammonium nitrate, ammonium hexanitratocerate, 4, crystallization from nitric acid was one purification method. Cerium, 4, nitrate was more readily extractable into certain solvents than the trivalent lanthanides. However, modern practice in China seems to be to do purification of cerium by countercurrent solvent extraction, in its trivalent form, just like the other lanthanides. Cerium, 4, is a strong oxidant under acidic conditions, but stable under alkaline conditions. When it is cerium, 3, that becomes a strong reductant, easily oxidized by atmospheric oxygen. This ease of oxidation under alkaline conditions leads to the occasional geochemical parting of the ways between cerium and the trivalent light lanthanides under supergene weathering conditions, leading variously to the negative cerium anomaly, or to the formation of the mineral cerianite. Air oxidation of alkaline cerium, 3, is the most economical way to get to cerium, 4, which can then be handled in acid solution. Isotopes. 4 isotopes of cerium occur naturally. These are 140 Se, which makes up 88.5% of cerium on Earth. 142 Se, which makes up 11% of cerium on Earth. 138 Se, which makes up 0.3% of cerium on Earth, and 136A, which makes up 0.2% of cerium on Earth. However, only 140A is stable. 142A, 138A, and 136A have half-lives of 5A, 10-16 years, 1.5A, 10-15 years, and 70 trillion years respectively. Additionally, some isotopes of cerium occur naturally in trace amounts as the result of fission of uranium. 39 isotopes of cerium have been discovered. They range from 119Se to 157Se. Cerium also has 10 known nuclear isomers. Aside from the nearly stable isotopes, the longest-lived isotopes of cerium are 139Se and 144Se, which have half-lives on the order of 107 seconds. An additional 8 isotopes have half-lives greater than 1000 seconds. All but 16 isotopes of cerium have half-lives greater than 1 second. The least stable isotopes whose half-lives are known are 153Se, 154Se and 155Se. They have half-lives on the order of 10 to 7 seconds. All the isotopes lighter than 140Se decay by electron capture or I² plus decay. All the isotopes heavier than 140Se decay by I² decay. History: cerium was discovered in bastnäsite in Sweden by Jar paragraph N.S. Jacob Berzelius and Wilhelm Heisinger, and independently in Germany by Martin Heinrich Klaproth, both in 1803. Cerium was named by Berzelius after the dwarf planet Ceres, discovered 2 years earlier. As originally isolated, cerium was in the form of its oxide, and was named ceria, a term that is still used. The metal itself was too electropositive to be isolated by then current smelting technology, a characteristic of rare earth metals in general. After the development of electrochemistry by Humphrey Davy 5 years later, the earth soon yielded the metals they contained. Ceria, as isolated in 1803, contained all of the lanthanides present in the cerite ore from bastnäsite, Sweden, and thus only contained about 45% of what is now known to be pure ceria. It was not until Carl Gustaf Mosander succeeded in removing lanthana and edimia in the late 1830s, that ceria was obtained pure. Wilhelm Heisinger was a wealthy mine owner and amateur scientist, and sponsor of Berzelius. He owned or controlled the mine at bastnäsite, and had been trying for years to find out the composition of the abundant heavy gangue rock, now known as cerite, that he had in his mine. Mosander and his family lived for many years in the same house as Berzelius, and Mosander was undoubtedly persuaded by Berzelius to investigate ceria further. When the rare earths were first discovered, since they were strong bases like the oxides of calcium or magnesium, they were thought to be divalent. Thus, cerric cerium was thought to be trivalent, and the oxidation state ratio was therefore thought to be 1.5. Berzelius was annoyed to keep on getting the correct ratio 1.33. In the late 1950s, the Lindsay Chemical Division of American Potash and Chemical Corporation of West Chicago, Illinois, then the largest producer of rare earths in the world, was offering cerium compounds in 2 purity ranges, commercial at 94–97% purity, and purified, at a reported 99.9+% purity. In their October 1, 1958 price list, 1 pound quantities of the oxides were priced at $3.30 or $8.10 respectively for the 2 purities. The per-pound price for 50-pound quantities were respectively $1.95 or $4.95 for the 2 grades. Cerium's salts were proportionately cheaper, reflecting their lower net content of oxide. Occurrence: cerium is the most abundant of the rare earth elements, making up about 0.0046% of the Earth's crust by weight. It is found in a number of minerals including alanitia euro, Ca, Se, La, Y, 2, Al, Fe, 3, CO4, 3, OH, monazite Po4, bastnäsite Co3F, hydroxylbastnäsite Co3, OH, F, rhabdophane Po4H2O, zircon, and sinchizite Ca, Se, La, Nd, Y, CO3, 2F. Monazite and bastnäsite are presently the two most important sources of cerium. Large deposits of monazite, alunite, and bastnäsite will supply cerium, thorium, and other rare earth metals for many years to come. Cerium content in the soil varies between 2 and 150 parts per million, with an average of 50 ppm. Seawater contains 1.5 parts per trillion of cerium. There is almost no cerium in the atmosphere. Production: the mineral mixtures are crushed, ground and treated with hot concentrated sulfuric acid to produce water-soluble sulfates of rare earths. The acidic filtrates are partially neutralized with sodium hydroxide to penthouse 3 4. Thorium precipitates out of solution as hydroxide and is removed. After that, the solution is treated with ammonium oxalate to convert rare earths into their insoluble oxalates. The oxalates are converted to oxides by annealing. The oxides are dissolved in nitric acid that excludes one of the main components, cerium, whose salts are insoluble in HNO3. Metallic cerium is prepared by metallothermic reduction techniques, such as by reducing cerium fluoride or chloride with calcium, or by electrolysis of the molten Ceres chloride or other Ceres halides. The metallothermic technique is used to produce high-purity cerium. The annual world production of cerium is in the region of 24,000 mt. Say atoms can be doubly encapsulated in C82 fluorines and then in carbon nanotubes. This procedure allows studying individual Say atoms. It can also be used for controlled doping of carbon pairopods with Say electrons for electronic applications, owing to the strong electron affinity of fluorines. Applications: a traditional use of cerium was in the pyrophoric ferrocerium alloy used for lighter flints. Because of the high affinity of cerium to sulfur and oxygen, cerium itself or as misch metal is used in various aluminum alloys and iron alloys. In steels, cerium degasifies and can help reduce sulfides and oxides, and it is a precipitation hardening agent in stainless steel. Adding cerium to cast irons opposes graphitization and produces a malleable iron. Addition of 3 4% of cerium to magnesium alloys, along with 0.2 0.6% zirconium, helps refine the grain and give sound casting of complex shapes. It also adds heat resistance to magnesium castings. Cerium metal is sometimes added to aluminum to improve aluminum's corrosion resistance. Cerium alloys are used in permanent magnets, and in tungsten electrodes for gas tungsten arc welding. Cerium is used in carbon arc lighting, especially in the motion picture industry. CMP Ceria is the most widely used compound of cerium. The main application of ceria is as a polishing compounds, for example chemical-mechanical planarization. In this application, ceria dioxide has replaced other metal oxides for the production of high-quality optical surfaces. Catalysis Another important use of cerium oxide is in a hydrocarbon catalyst in self-cleaning ovens, incorporated into oven walls and as a petroleum cracking catalyst in petroleum refining. Major automotive applications for cerium oxide are as a catalytic converter for the oxidation of CO and NOx emissions in the exhaust gases from motor vehicles. Niche applications The photostability of pigments can be enhanced by the addition of cerium. It provides pigments with light fastness and prevents clear polymers from darkening in sunlight. Television glass plates are subject to electron bombardment, which tends to darken them by creation of F-center color centers. This effect is suppressed by addition of cerium oxide. Cerium is also an essential component of phosphors used in TV screens and fluorescent lamps. Cerium sulfide forms a red pigment that stays stable up to 350 degrees Celsius. The pigment is a non-toxic alternative to cadmium sulfide pigments. Cerium oxide is used in incandescent gas mantles, such as the Welsbach mantle, where it was combined with thorium, lanthanum, magnesium, or yttrium oxides. Cerium sulfate is used as a volumetric oxidizing agent in quantitative analysis. Cerric ammonium nitrate is an oxidant in organic chemistry and in etching electronic components, and as a primary standard for quantitative analysis. Biological role: cerium can act similar to calcium in organisms, so accumulates in bones in small amounts. Cerium is also found in small amounts in tobacco plants, barley, and the wood of beech trees. However, very little cerium accumulates in the food chain. Human blood contains 0.001 ppm, human bones contain 3 ppm, and human tissue contains 0.3 ppm of cerium. There is a total of 40 mg of cerium in a typical 70 kg human. Humans typically consume less than a milligram per day of cerium. Cerium are the cofactor for the methanol dehydrogenase of the methanotrophic bacterium Methylacidophyllum fumariolicum solvi. Cerium salts can stimulate metabolism. Precautions: cerium, like all rare earth metals, is of low to moderate toxicity. Cerium is a strong reducing agent and ignites spontaneously in air at 65 to 80 degrees Celsius. Fumes from cerium fires are toxic. Water should not be used to stop cerium fires, as cerium reacts with water to produce hydrogen gas. Workers exposed to cerium have experienced itching, sensitivity to heat, and skin lesions. Cerium is not toxic when consumed orally, but animals injected with large doses of cerium have died due to cardiovascular collapse. Cerium is more dangerous to aquatic organisms, on account of being damaging to cell membranes. Cerium, 4, oxide is a powerful oxidizing agent at high temperatures and will react with combustible organic materials. While cerium is not radioactive, the impure commercial grade may contain traces of thorium, which is weakly radioactive. See also, organocerium chemistry. References. External links: its elemental the element cerium, cerium properties and applications, Chemistry and its Element podcast from the Royal Society of Chemistry's Chemistry World, Cerium.